Okay, so I will be talking about modeling the wave generation processes in the inner magnetosphere and the challenges that we are facing. As we discussed yesterday, we need to develop a global model of the wave excitation, and we have various types of waves like EMIC waves, chorus waves, magnetosonic waves. And the difficulty comes from the fact that we need to use kinetic theory in order to solve for the injection and transport and acceleration of the particles, and then the trapping in the near Earth region and the loss of the particles. So we need to know the distribution function of the particles as function of energy and pitch angle. And also we have to use self-consistent treatment because once the waves are excited, they will also feedback, scatter the particles. And I think we are right now in a very fortunate time for this field because of the Van Allen probes, which are flying exactly through the inner magnetosphere and the region where these waves are excited, so we can use for validation of the models. And I would like to acknowledge my collaborators from Los Alamos, also from UCLA, who have contributed to this work. So Richard this morning showed the first magnetic storm models and what was the thinking in the 70s. The formation of, during the storm, the injection of the particles and the excitation of the waves. And it is pretty much the same processes we are discussing today. The outstanding questions that we need to solve are now more quantitative. So what is the spatial extent of the waves? How do they change during a storm? Because we would like to quantify the effect on the ring current and the radiation belts. So the models and the results that I will be discussing are for models in the inner magnetosphere. So we use usually as a boundary conditions geosynchronous data or data provided from MHD models. And one thing I wanted to point out that geosynchronous data is available again. And if somebody wants to use, please contact Mike Henderson, and he is the person that will be providing the data to the community. So the plasma sheet source population, as we talked yesterday, is depending on solar and geomagnetic activity, as is shown here also in this recent study by Chris Muikis from cluster data. The contribution of oxygen ions increase with solar and geomagnetic activity, and this ion composition is very important to be taken into account because it leads to different decay scales in the ring current. So another interesting study I wanted to show here, the one done by Janet Kozira in the 80s. She looked at the generation of different of the EMIC waves and pointed out that it depends a lot on the cold plasma. So here on the left-hand side is for 10 per cc cold plasma, and on the right-hand side is for 500. So the wave growth increases significantly in the cold plasma, so that is why nowadays at the effect of the plasmaspheric plumes when we do the simulations. And also she pointed out the importance of the ion composition. So for example, here, if we consider both proton, helium, and oxygen ions, there is excitation in two waves. Mode 1 is the EMIC helium plus band below the helium gyro frequency, and the other one is the oxygen band below the oxygen gyro frequency. And the results that I will be showing are mostly in this frequency band. So when I got involved in this field, it was in the 1990s, and at that time we didn't know how important are the waves. So the task that I was given as a PhD student was to look at the wave-particle interactions and how to include them in the global models and to see if they have any effect on the global distribution of the ring current and ions and electrons. So the first study what we did was to compare lifetimes from charge exchange and in this case EMIC wave scattering, and we found that the waves should be effective in the higher energy range above 50 keV. So this was a good indication that it is worth it to work on this problem. And then incorporating pitch angle and energy scattering using quasi-linear theory, I was able to show that indeed there was some effect that you could look at the distribution function, and it was also shown that the pitch angle scattering by the EMIC wave have a larger effect than the energy diffusion, and it was also important to consider not only the local effect, but the drift and the transport of the ions through the region. So later, after the launch of IMAGE and observation of the suborbital proton arcs, what we did together with Maria Spasojevic, work on the event of suborbital proton arc observation here during June 2001. This was this detached arc in the afternoon region, and overlapping with the extended plasmaspheric plume. So what we did some simulation of the ring current evolution during this period, and calculated the excitation of the EMIC waves during this, so this is hourly intervals. We found that the growth is EMIC wave, large wave growth here in the afternoon sector. And when we calculated the precipitation of 10 to 40 keV ring current ions, if we do not include EMIC wave scattering, and if we do include EMIC wave scattering, we see that the EMIC waves cause this extended precipitation in the afternoon region, similar location and similar time dependence as the proton arc. So we claim that this is good mechanism to explain the proton arc observations. So here I would like to show a more recent study together with Lengjin Chen that we did working on the GEM Challenge events for this moderate period of June 2001. And again, we will be focusing on these 4 times during this event during June 9, when there were FUV images of proton aurora, and again trying to see if we can reproduce those. So we did the simulation now with our more developed ring current model with a self-consistent magnetic field. And here are comparisons of the simulation and HINA data, which were also available. So this is part of the reason why we selected this event for detailed study. And looking at the global distribution of the proton fluxes during the storm, the perpendicular and the parallel flux. And the fluxes are not very intense in this case because this is a moderate storm period. It was about minus 40 nanotesla. But we do see the enhancement here in the dusk side as it is seen in HINA data of the perpendicular flux. In the parallel flux, in this case, this is the simulation without the EMIC waves. So once we have that simulation, I expect that we will be able to reproduce this enhancement of the parallel flux because, as you will see in the next slide, this is where we do predict EMIC wave excitation. So this is looking exactly at the 4 time snapshots during that period. On top is the simulation of the plasma pulse position with our model, and with the purple is the model, and the solid is the inferred position from image EUV data, which shows a reasonable agreement. Then the pressure, the ring current proton pressure, increase with the development of the storm here in the pre-midnight region. This is the anisotropy of the ring current. So now, once we have included a non-dipolar magnetic field and transport in a more realistic magnetic field, we see the increase of the anisotropy here at the larger L shells, and also we see the excitation of the MIC waves. Longin made this simulation using the hot ray tracing model, calculating the helium plus band EMIC wave gain and showing a very large wave excitation in the afternoon region. So comparing this wave excitation with the proton aurora observations, here we are plotting with a red line the prediction of the RAM-SCB model, and we see that the proton aurora sub-aurora is extending at larger L shells, so that is why now we are working on extending the model beyond geosynchronous, but still it is a good agreement with when the FUV subaurora proton images are observed. So, as I said, our model is coupled ring current model, kinetic ring current model with 3D model that takes the pressure from the ring current and calculates the magnetic field. Now we are working at extending the model to 9RE, and in this case we are using an empirical plasma sheet model from Tsiganenko and Mukai as a driver from the plasma sheet, and also using ion composition after Muikis et al. At the outer boundary condition. So here I wanted to show some examples of a simulation of a storm during the Van Allen probe time. So this was a storm on November 1st, 2012. The minimum DST was around minus 60 nanotesla, and at that time the Van Allen probes were orbiting on the downside orbit. And here are the plasma sheet data predicted by the model of Tsiganenko and Mukai. And I wanted to point your attention that there is increased density during the first storm period, and then it decreases actually during the main phase. And this will affect the results. So here is the comparison of our model with data from the Van Allen probes. So in this case, we show a comparison to cover the all energy range of the ring current simulation. We use data from MagEyes up to 350, from 50 to 350 keV, and the HOPE data from about, I believe 20, I forgot, 20 keV to, anyway, no, it's below, it's above 1 keV, from 1 keV to from 1 keV to 50 keV, yes. And looking, these are plots similar to what Lou showed during storm. So this is 1 day. The time scale here is hours, and when near perigee, we are outside of the model domain, are this white stripe inside of L2. Near apogee, we see the decrease of the fluxes at high radial distances, and also we see these injections from MagEyes data continuing into HOPE data, showing a very good resolution of the data and good agreement between the two instruments. And these are the model simulation. Now we have implemented the latest version of the Weimar 2005 electric field, and we are able to reproduce the higher energy distribution of the Mach-I's. The lower energy distribution of the Hope instruments, we reproduce the increases here during the storm main phase. This injection, okay. So the injection we reproduce at the higher end. We don't reproduce this filling of the stagnation deep at the lower L shells, which indicates that the Weimar model is not strong enough to inject the particles to lower L shells. Here we show a simulation with Volon-Stern, which showed a little bit higher fluxes at the low energy, but not too much increases. So we made a test simulation using a boundary conditions, fixed boundary conditions of 0.5 per cc, which were observed during the beginning of the, which were predicted during the beginning of the storm. And here we saw a better increase of the fluxes, indicating that probably the Tsigonenko and Mukai model in this case underestimated the plasma sheet density during the later period of the storm. And also because our model calculates the magnetic field, we compare the calculation of the magnetic field with the emphasis magnetometer data for the three different components, and here showing the BZ component. With the black line is the observation, with the red line is the simulation, and with the green line is the dipolar field. So we clearly show that even during a moderate storm like this one, the magnetic field on the night side, as is shown also here in these plots, is significantly depressed, and the depression reaches down to L4. So during the same storm period, we calculated the excitation of the EMIC waves, which was one of the main reasons why we extended the model using the plasmaspheric density, again with two different electric field models, Weimar 2005 or Volon-Stern. So we saw a large enhancement, especially using the Weimar model on the night side and the dusk side area. So this is where we saw that the model was under-predicting the precipitation of the image FUV data. So we think that it is a good indication that the EMIC waves are excited at larger L shells, and it will have effect on the precipitation of both ions and electrons. And finally, one more slide I wanted to show was about the ring current electron instabilities, because the ring current electrons, as it was discussed in the morning, are, when they are anisotropic, they lead to the excitation of the chorus waves. So here we did a simulation of the ring current electron instability during October storm 2002. And again, comparing, so in these plots is a different view. The days, noon is on the top, and midnight is on the bottom. So we can compare with these observations from Meredith et al. And again, using non-dipolar magnetic field, our model predicts a large region of anisotropy of chorus waves. In this case, it is on the day side in the morning sector, and it is in agreement with the lower band excitation, the lower band observation of chorus. This is a statistical picture from Meredith et al., where they show that these chorus waves are mostly observed in the day side, dawn side region. So to summarize, I think we have made significant advancements And I think that now it is well believed that plasma waves do play an important role in the particle acceleration and loss in the inner magnetosphere. So the recent simulations that we have done with our RAM-SEB model during storm time show that we can get EMIC and Whistler mode waves excited, so there is sufficient free energy for the excitation of these waves in the ring current ion and electron populations. And the growth rate of EMIC waves is maximum near the dusk side, while for Whistler mode waves is maximum due to the electron injection and the eastward drift on the dawn side. So, and with the expanded model, we see even bigger region extending to higher L shell of this wave excitation. So we have achieved advancement in the modeling, and we can reproduce the statistical patterns of the observations. And what I think we need to work now is to do some more specific simulations and to be able to do more model validation with comparison with Van Allen probes data. And I would like to thank the support from RBSP.
Questions for Vanya? Yes, Stephen.
Steve.
I was just curious, you had a few slides of image proton data. Where do you get those from?
Pardon?
You had a slide with, at the bottom there were a bunch of image proton auroral data. And I was just kind of, I haven't seen it like that before.
Well, this is what Maria Spasojevic provided, the proton aurora from image
okay.
FUV.
Oh, she did, okay. Well, it just didn't look like the stuff we have been putting out, so.
Oh, okay.
Well, kind of probably a good reason.
Okay, any other questions? Okay, if not, thank you, Vanya.